Now, we're going to take up one more problem, the problem number 26 on the overhanging beam. For the beam shown in figure, draw the SFD and BMD and mark the values of salient points. Locate the position of point of counterflexure, if any. So here we have an overhanging beam, which is B at C, which overhangs by 3 meters on the left hand side and also 3 meters on the right hand side. So at the point A, we can see the load is acting downwards, which is RAV. So which is, we need to find out. Then we have the clockwise couple, which is 30 kilonewton meter at the point A. And you have the load at B. We have the load at B, which is UDL, which is 30 kilonewton meter. That is, just you have the point B here. Then we have the load at C, which will be RCV, which is the support reaction. RAV, we have the support reaction. Initially, we are thinking that it is acting downward, acting upwards. And also 50 kilonewton, which is acting downwards at the point D. Between B and D, you have a uniformly distributed load of 30 kilonewton per meter for a span of 6 meters. So to do that, so here, to analyze this, first we need to go for the support reactions. So what are the support reactions? Taking the moment about the point A, that is with respect to this point. So what we have, RCV into 6 will be equal to plus 30 plus 50 into 9 plus 30 into 3 into 30 into 6 by 2 plus 3. So that is RCV into 6 will be equal to 50 into the entire distance with respect to the beam, that is 50 into 9 plus 30 into the UDL is for the span of 6 meters. So 30 into 6 into the distance of center of gravity, the distance of the point from the moment point. So till UDL you have 30 into 6 into, open the bracket, 6 by 2. So that distance with respect to the point A will be equal to 3 plus 3. So that means 6 by 2 plus 3. Plus you have a clockwise couple, which is at the point A will be equal to plus 30. On simplification, therefore, you will going to get it as RCV, which is equal to 260 kilonewton. But also we know the sum of the vertical reactions will be equal. A vertical reaction which is acting upwards will be equal to the sum of the vertical reactions acting downwards. So once you are considering this, here initially we are considering RAV to acting upwards. So therefore, RAV plus RCV will be equal to, now here we have 30 into 6 plus 50, we are acting downwards, the load acting downwards. So you know the value of RCV, which is equal to 260. So taking that to the right hand side, so you will going to get 30 into 6 plus 50, which will be 180 plus 50, which is 230. Minus 260, therefore you will going to get minus 30 kilonewton, which will going to be RAV. So instead of, since you have the negative value, therefore at the point A is load is acting downwards, that is the reaction at the point A in the vertical direction will be equal to 30 kilonewton acting downwards because it is having the negative sign. Now we are going to get the shear force diagram. So once we are considering the shear force, what is the SF at the point A? SF at the point A will going to be, as the load is acting downwards. So if the load is acting upward, then it becomes positive. So since it is load acting downwards, it's negative. So SF at A will be equal to minus 30 kilonewton. So between A and B, as there is no other vertical load which is acting, so SF at B will be equal to minus 30 kilonewton. So when you are considering SF at the point C, so SF at the point C, we have two loads are acting. One is the vertical load which is acting at the RCV, which is equal to 260 kilonewton, and the other one is UDL, which is acting till to the point C. So if you are considering the section to just on the left hand side of C, so you will going to consider only up to the shear force of the load. So SF at C will be equal to, so what happens, you will going to get it as minus 30 into 3 plus 260. So first initially you will going to get it as minus 30 into 3 because only up to the point of UDL you will going to consider. So then it will be 90 minus 30, which will be minus 120. So you will going to get it as minus 120 SF at C just on the left hand side. If you are considering SF at exactly at this point, so now at that point we need to consider the vertical reaction, which is plus 260 kilonewton. So since it is plus 60, so then what happens? Minus 30 into 3 becomes 90, minus 30 minus 90 minus 30, which is minus 120 plus 260. You will going to get it as plus 140. That means SF varies from SF suddenly increases from minus 120 to plus 140 in the positive direction because due to the reaction at the point C. SF just on the left hand side of D. So when you are considering the SF just on the left hand side of D, so you will going to get it as plus 140 minus 30 into 3, which becomes plus 50. So just on left hand side, SF at the point D will be equal to plus 50 kilonewton. So this is how you will going to get this SFD. So SF at A is minus 30 kilonewton. Between A and B, it remains constant at 30 kilonewton. We don't have the vertical reaction at the point B in the upward direction. So then SF just on the left hand side of C will be minus 30 into 3, which is minus 90 minus 30, which is minus 120. So it varies from minus 30 kilonewton to minus 120 kilonewton. Further it drops down. So SF at C, what happens? Because due to the vertical load which is acting upwards, which is positive, so then it will going to be, it increases from minus 120 kilonewton to plus 140 kilonewton. SF just on the left hand side of D, which will going to be 140 minus 30 into 3 becomes 90. 140 minus 90 becomes 50 kilonewton. So SF at D also, which is going to remain same 50 kilonewton. As it varies from 140 kilonewton to 50 kilonewton, since it is a uniformly distributed load, so the variation of the line will going to be is a linear line. So this is how we can give the explanation between A and B, which is already explained. It is a constant at minus 30 kilonewton. And then SF varies from minus 30 kilonewton to minus 120 kilonewton linearly, and then changes suddenly to plus 140 kilonewton due to the point load at C, or due to the reaction at the point C. And SF varies from 140 kilonewton to 50 kilonewton positive linearly. So this is how you will be able to analyze the shear force diagram. Now we will going to consider the bending moment diagram. So what is the bending moment at the point A? So the bending moment at the point A, as it sags, so because of the clockwise direction, it sags there. So therefore, you will going to get the beam has to be positive plus 30 kilonewton meter. So BM at B will be equal to plus 30 kilonewton minus 30 into 3, because it hogs as the point is acting, as the load is acting downwards. So the tendency of the beam to bend in the downward direction, so it becomes hogging. So therefore it becomes negative. So plus 30 minus 30 into 3 will going to give you plus 60 kilonewton meter. Now when you are considering the bending moment at the point C, so that will going to be plus 30 minus 30 into 6, then minus 30 into 3 into 3 by 2. So on simplification, you will going to get it as minus 285 kilonewton meter. Similarly, BM at the point D will be equal to plus 30 minus 30 into 9 plus 30, again minus 30 into 6 by 2, minus 30 into 6 by 2. Again, since the load is acting at the RCV, acting upwards, it becomes positive. So plus 260 into 3. So on simplification, you will going to get that value as 0. So this is how you will be able to get the shear force bending moment diagram plotting. So how I will going to get here the shear force, the bending moment at the point A is due to the couple effect. It's going to have a positive value, which is in the clockwise direction. So then we have as the load, we can see the bending moment at the point B is changing from positive to negative at this point. And then from point B, further it drops down to minus 285 kilonewton meter at the point C, because due to the parabolic effect. And at the point D, it becomes 0. So again, you have joined between the parabolic curve, because between B and D, the load acting is uniformly distributed load. Therefore, you will going to get the parabolic curve on either of these two curves. So this is how you will be able to analyze this. Now, what happens is, as the bending moment diagram, you can see the bending moment is changing its sign from positive to negative at this point. So that point is called as point of contraflexure. As in the problem, he says, locate the point of contraflexure, if any. It is the point where the bending moment changes its sign. So let capital E, which I have not shown, be the point at a distance of x meters from A. So where the bending moment changes its sign. So what will going to be the bending moment at the point E? The bending moment at the point E will be equal to 0, because as the load, as the bending moment drops down from plus 30 kilonewton meter at the point A to minus 60 kilonewton meter at the point B. As there is the change in sign from the positive to negative, therefore you will going to get the point of contraflexure. So we are considering that distance as x meters from E. So what is the bending moment at the point E? As the bending moment is changing its sign from positive to negative, in other words, it's crossing the reference line. So therefore, at the reference line where the line is the bending moment line is crossing, that point will going to be 0. So if you are considering that, then BM at T will be equal to 0. Plus, so plus 30 minus 30 into x will be equal to 0. So therefore, x will be equal to 1 meters. So therefore, the point of contraflexure is at 1 meters from E. So this is how you will be able to analyze and find out the support reactions and the shear force diagram and the bending moment diagram, and also the point of contraflexure, which is 1 meters from E. So this is how you will be able to solve this particular problem. Thank you.